So first, we'll start with the session because we already lost some time. So I would like to ask our HOD, Dr. B.R. Patugundi sir, just to welcome this all the participants. Sir, please, you can. Patugundi sir.
Sir. For everybody, the department of SCBIT series of webinars in this and also in the future also. So the first of its kind is today the webinar by Dr. Manmohan Kalgal, Technical Advisor, Ultratech Cement, Bangalore. He is going to speak on application of applications from I
Sir, you have to not all.
He served in the Department of Civil Engineering, MS Ramaya Institute of Technology, for a period of 22 years, starting from 1980 to 2002, in different roles, starting from assistant professor to professor level. He completed his PhD from Indian Institute of Science, Bangalore. In his professional career, he served as a general manager, technical and marketing in BBR India Private Limited from 2003 to 2007. Then he served as a vice president and head building products division from July 2007 to 2010. Later, he became senior vice president and joint president and head technical services from 2010 to 2016. Later, he served as a vice president in Asian Concrete Federation from 2017 to 2018. He was elected as the president of Indian Concrete Institute, which has 38 centers pan India with more than 11,000 members for the period of 2015 to 2017. Presently, he is serving as a technical advisor, Ultratech Cements Private Limited, Bangalore. Also, he is associated with Ultratech Cements Private Limited since from last 13 years. We are very much fortunate enough to have Dr. Manmohan Kalgal sir as a speaker for this webinar. I once again welcome Kalgal sir. Now I would like to hand over the session to Manmohan Kalgal sir. Sir, you can proceed with your talk.
Okay, thank you, Deepak. Am I audible?
Yes. Yes, sir. Yes, sir.
yes, sir.
Yeah. Good morning, friends. I am informed that majority of you are students of civil engineering at SGBIT, and there are a couple of faculty members probably, and a few others also. So, a very good morning once again, and today we'll be discussing on this topic of application of pre-stressed and precast concrete in the building sector. So, if there's any disturbance, I'm not able to hear, I request Deepak Patil to butt in and tell me that my audio is off or the video is off or whatever. So,
Yes, sir. Yes, sir.
since this is meant for students, I am starting with a little bit of recap of what students would have studied or would have been studying. And I'm also told that there are 6 semester students, so they would not have probably studied pre-stressed concrete. But then I'll start from the initial, that is, we start from the preliminaries itself. That is, we know that we are using plain cement concrete, which is very strong in compression but weak in tension. But why are we talking about this tension? This tension is coming from where? So if you take a member which is in bending, you can see very clearly that the bottom surface is now in tension because of the bending stresses. So it is natural for us to write in the kind of figure which I have shown here at the bottom of this particular figure, that this represents the tensile forces. The area of this will give you the tensile forces, and this will be the compressive forces. So a force which is compressive at the top and becomes tensile at the bottom has to reduce and become zero somewhere. So the place where it becomes zero is called the neutral surface, and this is also taught to you by your teachers. So if you look at that in 2 dimension, if I write a sketch, a member which is subjected to a vertical load in the center and supported on either ends is going to experience tension at the bottom and compression at the top, as you can see there. So this is how we represent a stress diagram. the tension is at the bottom and the compression is at the top. So when we subject a concrete beam, which is made of plain cement concrete, to an axial, to a transverse load in the center like this, you will see that at the bottom where there is tension, because I said concrete is weak in tension, it starts developing a small crack. Now, this crack will happen when the tensile capacity of the concrete is, let us say, X, and the tension that is coming at that particular surface also reaches X, then you get a crack which is initiated. So the minute that crack is initiated, because concrete is weak in tension, the beam will break into two. So this kind of experiment you would have done in the laboratory with either single point loading or 2 points loading. Now, people thought that we will use steel to take care of this tension because concrete is not capable of taking. And why steel was better for? Because it is very strong and it is ductile in tension, and it has thermal coefficient expansion similar to that of concrete, and it can be easily bent and placed whichever way you want it, and is readily available and relatively inexpensive. Also, it bonds very well with concrete, and now with the reinforcement which is ribbed, the bond is excellent with concrete. What is that concrete has to reach its tensile capacity and it is about to crack, and a small crack in it's only then that the tension transferred to steel. Say, okay, I will take care of tension, and from there on, the micro crack which has developed will not further grow, but the steel will start taking the tension. So this is the role of the reinforcement, and hence such a concrete is called as reinforced concrete. So you can see here a concrete beam which is having steel at the bottom, and also in the cross section you can see that there are 3 rods which are placed at the bottom. So when we subject this to a vertical load, the tension is now taken by the steel. As you can see, it is taken as steel. That means this is the area of the steel and the tensile stress carrying capacity of the steel, which will determine how much tensile force it can take. The compressive force, of course, is the maximum compressive stress that it can take, and the area of the compressive stress diagram will give you the total compression that it can take. So there are different ways of looking at the stress distribution in the concrete, whether it is triangular, rectangular, parabolic, and so on and so forth. I'm not getting into this. All of this you have studied. So in a reinforced concrete, when you start loading it centrally, what happens is first one crack will open, then it will transfer the stress to the steel. But there are other areas where the concrete has not yet cracked. They also start developing small cracks and start transferring the tensile stresses that are there to the steel. Now, as we increase the load, the crack in the center starts becoming wider and wider. And once the steel reaches its capacity, the steel starts yielding and the beam tends to bend and fail, or it can't take any further load. So this is the typical behavior of a reinforced concrete. Now, when we talk of pre-stressing, what is pre-stressing after all? Pre-stressing. That means we are stressing it before it is brought into use. So this is a method by which we create internal stresses which are permanent in a structural element. So why do we do this? We do this because we want these stresses to counteract the stress which is going to come when the element is in use. The teachers who are teaching Prestress concrete normally give the example of a lifting of row of books. Suppose you have a set of books, you want it is there on your rack and you want to lift it. If you put hands on both sides and try to lift, it will not come up. Only when you apply a pressure towards the center, and then you will see that this particular section now becomes strong to be lifted as a whole. So this lifting of the books is a function of how much pressure you put inside. Also, if you apply sufficient amount of pressure, you can not only lift the set of books, you can even keep some books on top and lift it along with it, which is in the tension in the concrete. Now again, we'll come back to this picture. The pre-compression forces are shown by two horizontal arrows there. And now if I apply a vertical load, it will induce tension, but it has to overcome the compressive stresses which are already built in there. So this particular compressive stress will have to be overcome by the tensile stresses caused due to bending. Then it becomes zero, then it can become tension, and only then it will crack. But look at what happens on the compression side. Already there was a pre-compression. Due to bending, there is a compression. So that compression plus this compression added will become a larger compression at the top. And if the compression is sufficient enough and more than the tension that is likely to come due to bending, you can keep the whole section in compression. So I'm not going to explain any further on this because that is not the aim of this particular lecture. I just wanted you to know conceptually what this particular pre-stressing and pre-stress concrete is all about. My fundamental focus will be more on precasting and its application along with pre-stressing in the building sector. There is another concept which I just want to draw your attention to. This is called concept of load balancing. Now you see a line which is shown here. I hope you can see my cursor. This line, suppose I were to put the cable inside the concrete like this, a cable which is flexible but at the same time extremely strong. If we can put it in this particular shape or in this particular shape inside the concrete, inside a tubing, in the tube if I put this steel wire and before after the concrete becomes hard, if I can pull this particular wire and lock it from not coming or not becoming its original length, suppose I pull this wire within its elastic limit. If I pull a rubber band and leave it, it goes back to its original shape, right? Similarly, if I have a high tensile steel wire, if I pull it within the elastic limit and release it, it goes back to its original length. Now, if I prevent it from going to its original length by locking it at the two ends after stretching, then the wire would want to become straight and hence tries to lift up. So there are two ways of looking at it. One is it wants to get back to its original length, so it is pressing on the sides. Or in other way, if you can look at it, it wants to straighten itself and hence is pressing upwards. So if I apply sufficient pull, I can make it such that the upward pressure due to its urge to come back to its straight line is same as the load that is likely to come, which means I can have a zero deflection. So this is one of the methods of looking at pre-stress concrete. So when you come to principles of reinforcing, we saw in reinforced concrete that we put the steel wherever there is tension likely to come. So if you look at the diagram C, in this particular beam which is having three supports, in each span, in the middle at the bottom there will be tension, and on top of the second the support, at the top there will be tension. So if I were to use a reinforced concrete, I would have used steel at bottom of the two spans and also at the top of the central support. Now, if I come to post-tension beam or pre-stressed beam, what do? I pass a cable in such a way that the cable is present wherever there is likelihood of tension. Now, what this cable will do? This cable will actually create compression. That means if I am having a beam which is likely to get tension at the bottom, at the midspan, and tension at the top in the center of the support, I put a cable and create compression there. So when the actual load comes and tries to create tension, it has to first overcome the compression. So it is much superior in its behavior. Okay. So the advantages of prestress concrete is that the full cross section is used. The section is under compression most of the time, so it is generally crack free. It is more efficient, and because we are using the full section, smaller sizes can be used for the same stresses, so it will have lesser self weight. It becomes very important in very large spans, like let us say bridge girder. A bridge girder has such a huge span that the depth of the beam becomes too much if I were to use the RCC section. How do I increase the capacity of the RCC beam? I have to either increase the steel or increase the depth, right? So M is equal to QBD square. So D times square times the depth, the moment capacity increases. So in an RCC member, I keep on increasing depth. But when I increase depth, you should also realize that it will increase the dead weight, which will cause more moment and so on. So we would like to avoid such a situation by going in for pre-stress concrete, which has smaller sizes and lesser self-weight, and also much better capability to handle the deflection issues. It can also take overloads, because in a pre-stress concrete member, which you have designed for a load of, let us say, X, or for a bending moment of X ton meter, if it is exceeding, then the stresses in the in the flexural side can become zero or can become negative, and a small crack can open. But if occasional that overload is removed, immediately the crack will close because the compression will take it. So these are advantages of the pre-stress concrete. I also mentioned about the reduced deflection, because you can create an upward deflection slightly by pre-stressing. Okay, what is used in pre-stress concrete? The same concrete is used, but only you must remember that in the top side there was compression plus compression, so a higher compression. So we tend to use higher grades of concretes like M35, M40, M45, and so on. So this is required to tolerate the high stresses and also to minimize a phenomena called creep. What is creep? Creep is a deformation under sustained load. So we are keeping compression on throughout its life. So if I keep compression on throughout the life, then it is possible that the member may shorten due to this creep. So creep is also possible in steel. The steel wire, you are keeping it in tension for a long time. Take the example of the rubber band. If I pull the rubber band and leave it, it comes back to its original. Now, if I were to keep the rubber band pulled, that is, let us say I put it around a roll of drawing sheet and put it in my attic for 6 months. After 6 months, if I remove and see whether this rubber band will come back to its original, it will not come back. Why? It has relaxed. It has got sick of wanting to come back to its original. So this is called creep, or this is called relaxation. So in steel also, it is likely to relax because the stress will be on throughout the life of that structure, and the steel has a tendency to relax if the steel is having lesser strength. So we use a very high tensile steel here for two reasons. One is to avoid much of relaxation due to creep, and to tolerate very high stresses. Please remember, the steel has to be stressed within elastic limit so that it has an urge to come back. So if I use a very strong material, I can stretch to a larger force without exceeding the elastic limit. But we also use normal steel like Fe415 ordinary steel. This we use for enhancing ultimate strength, or to use as shear reinforcement, and also to prevent some destructive bursting which might happen at the anchorages. Now I come to the main thing called the precast concrete. Just like what I mentioned about pre-stressed, here is precast. Pre means earlier, cast means it is cast earlier. So a concrete which is cast earlier, that is a product which is made out of concrete which is cast earlier in a reusable mold or formwork and then cured in a controlled environment, transported to the construction site and kept in that position is called a precast member. So, in contrast, a standard concrete member that we are accustomed to in our buildings is actually poured at site in specific molds and they are cured at site. So, here we cast the concrete elsewhere or not in the place where it is supposed to be and do it in a factory kind of atmosphere. So, it is either reinforced concrete or it can be pre-stressed concrete. Precast simply means it is cast earlier. So pre-stressed or reinforced depends on what kind of forces that are there in it. So this precast concrete is generally made in a factory that is off-site, or it can also be cast on-site somewhere down below on the ground if you have sufficient space in a building products from a long distance, and if you have space, you can do it at site also. So a better quality is obtained. Workers and supervisors are well trained and experienced. So you don't have different laborers working at different points of time. And also what is important is since the members are already cast and ready, you don't have to worry about the weather. Now in normal construction, if it rains, the construction will stop. Here, the construction can go on in rain also because the concrete is already hardened and it is strong enough to take the loads. So, site precast may or may not be adopted, but it is common to adopt it when the project volume is very large and setting up a plant at site is economical. Otherwise, the cost of setting up the plant at site may be prohibitive. So, what are the other reasons why you should go for precast? The first and fundamental reason why you go for precast is to achieve speed. So, when the structural precast elements are being cast at the factory, the other works like excavation, foundation, such other things can be carried out. Now, once the foundation is ready, the precast materials can be simply lifted to the side and it can be placed in the position that it is to be done. So, very quickly you can build the structure. So this will also reduce site congestion because you don't have to store all the aggregates, cement, sand, and so on at the site. Only you have to bring the precast materials, simply assemble it at site. This increase in speed also helps the finance costs because people might have taken loan and they might be due to pay EMIs. If the building is ready fast, then it is much better for the financial issues also. So quality and durability are automatically built in because precast is made under factory conditions. High strength concrete can be used. A very accurate placement of steel can be ensured. Very good finish can be done. So quality and durability will not be an issue in precast concrete. That's another reason why people go for precast. And the dimensional accuracy is so beautiful that it will fit just like a Lego, bit that is there. Any finish that you want, extremely superior finishes can be given. And because it is done in an environmentally controlled manufacturing condition, the entire concrete is quality certified. So we can also make sure that we can design and provide for very long spans and heavy loads. Large span systems can be done, load bearing walls can be prepared, and we can build in a lot of flexibility in the building by custom manufacturing the precast units and then incorporating it in the buildings. So it's an all-weather construction. It has low maintenance. It is environment friendly, and it is economical because of all these reasons. So I'm skipping a few slides, but some of the other benefits are that you can incorporate the door, window frames, the light fittings, the electrical conduits, pipe fittings, everything in the walls, and in the structural components before it comes to the site. So you save on time, you save on the issues of quality not being there and so on. Only thing is that you must plan everything properly and you must give that details to the precast manufacturer to incorporate doors, windows, and all other appurtenances there. So you can see that even the surface treatment, whatever that is required, can be incorporated by using the appropriate shuttering and form liners and so on. So the precast walls are generally thin and hence you get larger carpet area, which means economically for a person who is building and selling, he will get much larger carpet area to sell and hence it becomes economically viable for him. And better health and safety standards can also be incorporated. Let us look at some of the precast and pre-stressed concrete structural elements. Now these are typical elements from the left to right. The first one is a solid flat slab. The second one is a hollow core slab. That means a hollow slab, that means a slab which is capable of taking the load, but the central portion is, taken off. You know that the central portion is where the neutral surface is or the neutral axis is, and that's where you don't require much of concrete to handle any stresses. So if you can take out that much of concrete, it becomes lighter and more efficient. You may not be able to see uh, in the slide, but there are dots which are at the bottom of these slabs, which are actually cables, which are pre-stressing cables. So by pre-stressing, you can also make the same slab to span larger spans, or it can take larger loads. Or for a given load and span, you can have a thinner member. The third one which you can see is a slab with a beam built in. So you can build directly the slab and beam as a panel and you can come and assemble it. So you will have series of beams and a slab which is already built in on top. Or you can look at the last one on the right side. It is a single beam with a larger slab on the top. So when you put this kind of slabs in place, obviously you will realize that there will be joints in between these slab panels. So what is normally done is, once this is assembled, on top of this they put a thin weld mesh or a wire mesh and they put a concrete of about 2 inches or 3 inches, that is 75 mm, which is called as screed concrete, which will act as a composite material, but also it will prevent leakage and such other issues, right? I hope I am able to be heard clearly. Am I audible clearly?
Yes, sir. Yes, sir. You are audible, sir. Clear. It is very clear.
Okay. Now you can see here those hollow core slabs which are stacked in a factory. They can have different depths, different hole sizes, depending on what span and what load it is designed for. Okay. So these are precast beams and girders. You will see that the gray portion, that is actually a precast concrete which is already there. These are rectangular beams, L-shaped beams, inverted T beams, AASHTO beams and things like that. All of them have on top some portion of the shear reinforcement or the links which are projecting. Why are they projecting? Once you assemble these beams, on top you may put the slab in situ. That is, at the same place where the slab is to be, there itself you may cast the slab. So when you cast the slab at site or in situ, the shear links which are there projecting on the top will enmesh with the slab reinforcement and the whole system will become a structural load carrying system. Now you can see here these inverted T-beams are ready at the site in a precast. On the precast columns, the precast beams are placed. Now using this, on top of this, either a precast hollow core slab can be brought and connected or a slab can be cast in situ. Typically, a precast beam inverted On top, an inverted, ready-made hollow core slab is brought, and the junction is cast in situ. So this you can see a set of wall elements and the column elements standing at the side. So you can see that there are brackets or there are corbels in the column on which the beams or the slabs can come and sit, right? Now between the columns into a sleeve, the vertical elements or the slab elements will go and this will act as wall panels. So you can see here a few wall panels cast and ready for lifting and placing it there. So these walls can be hollow or it can be solid or it can even have a sandwich of some soft material or even thermal material built into this. Okay, so you can see here wall materials or wall panels can even have ribs to get higher stiffness and higher strength, and it can be in different shapes to accommodate doors, windows, and whatever architectural features that are there. The whole stairs can be precast and it can be placed whether it is in a stadium like structure which I have shown here or even in a house. You can bring the precast elements directly and keep that, and the staircase is ready within few hours. Now, how to design this? Of course, most of you are probably not into the designs in a very big way, but depending on the type of construction that you want to do, you can have different approaches to design. So the assembly will depend on what kind of concrete elements that you want to assemble and how much of it is precast, how much of it is cast in situ. What is important is you must remember that the same concept that slab will transfer the load to beam will transfer the load to columns will transfer the load to the foundation, same principles will be there. It's also possible that we might eliminate the beams, we might have or eliminate the columns, we may have the total wall system, that is the wall itself will take all the loads from the slabs and transfer to foundation. So the choice of roof and floor elements depends on the span requirements, and precast elements are used with other vertical load bearing elements. It may be a side cast system. Along with it, there can be a precast system. So you can see here a housing complex which is being built with precast walls and precast slabs and precast columns. You can see here a single story warehouse consisting of double T's. I showed you earlier, double T, which is having slab on top and the beam at the bottom. It is resting on the corbels which are there in again precast walls which are standing on the side. So this is a parking lot. You can see here again the assembly concept for a T-beam with a slab on top. The whole element can also be precast, for small things like watchman sheds, police chowkis, toilets, and such other things. You can even cast the whole building in one shot, put it on a truck, take it, and put it there. In fact, now in Ultratech, we are also trying to divide the house into two parts, cast that somewhere else, bring the two parts on a trailer, just connect the two, and the whole house is ready. So this kind of transportable precast houses are also being thought of. So either elements or it can be full house or at least part house. So in Bangalore, a company called Moore Living built ground plus 3 houses by this method of assembling two parts or full part of a house and simply lifting it, putting it in place. So that was a wonderful experience that we could see. It can also be applied in very large stadiums, arena, theater seatings, and so on, where large spans are there and you want to construct very fast. Precast is one of the ideal things to do. So there are other specialized applications like sound barrier walls, custom precast rings for chimney, storage and holding tanks, and interior firewalls, tunnel linings. Most of you are now aware of the metro that is coming up. In the metro, which is going underground, you would have realized that there is a tunnel which is being bored by a tunnel boring machine. After the tunnel is bored, at the openings or in the inside the tunnels, a liner is placed, and this is typically a precast section, as you can see on the top right hand side. As the tunnel boring machine moves, it will keep the these rings to or the segments to make it into a ring into which the trains will start moving. So these are pipe racks, even that is possible. These are ready-made tunnels or ready-made boxes which can be used as underpasses, which can be used as ducts, which can be used as crossovers, and so on and so forth. So culverts are another very good example for the precast. This is again an arch crossing in precast. Precast pavements. Now, even roads are being cast elsewhere. They're just bringing it and assembling it at site. So one night you close the traffic, put all the precast members there, stitch them together by pre-stressing, and next day morning you have the road ready. And this is an excellent application of precast in the road sector, of course not in the building sector. So these are some of the specialized applications like curb barriers, wheel stops, etc. So these are some more manholes, cattle feed trough, water tanks, and so on. Let me go quickly. We have another 10 minutes only. Uh, Probably I can go up to 15 minutes. Deepak?
Yes, sir. Yes, sir. Yes, sir. You can, sir. No problem.
Okay. This is railway sleepers and crossing panels in railway application. Twistless concrete sleepers, one of the earliest applications of precast. So this is a member which is precast and pre-stressed and just kept there, and the rail is assembled on top. So these are breakwater pots and compound walls. You can see how beautiful this compound wall looks, and the entire is a precast member. Just cast it, bring it, and slide it into the columns, and you have a col and a beautiful compound ready. When you have kilometers and kilometers of compound for, let us say, a large industrial area, precast is an ideal application. Now you may be thinking that precast will not be beautiful. You can see here, all of these are precast members which are so beautiful. So by adjusting the form liners, you can make sure that the concrete is looking very, very beautiful. Now there are a number of slides here, analysis and design aspects. I think someone is unmuted.
Yeah, yes, sir. Yes, sir. Please, somebody is unmute. Please unmute the audio. Hello.
So please unmute.
I request participants, those who have. Yes, sir. You can proceed now, sir.
Okay. Generally, the host has a facility to unmute everybody. I mean, mute everybody. Maybe that is not there. Okay. Now there are few slides on analysis and design aspects of buildings. I will not go into it much. I'll just stick to the applications. But what is important for us to know is that you require an integrated approach here in design. It cannot be done the way you do the normal buildings. Here, architects, structural engineers, precast concrete manufacturers, erection specialists, service providers all have to work from day one. Because in precast, if you want all the pipes to be built in, all the services to be built in, so service engineer should be there right in the beginning. Architectural features, whatever that needs to be done, architect has to be there from day one. Structural engineer, because he is going to analyze and design, he should be there from day one. The manufacturer of precast should be there from day one, because he will be able to say what sizes are possible, what sizes are not possible, what is not possible to be transported, and so on. The erection specialist will be there from day one, because he has to tell whether this can be lifted and kept, how it will be connected, and so on and so forth. So the entire group of precast specialists, structural engineers, architects, services, everybody has to look at the normal after the building is the shell is what walls, they will insert conduits and so on. Nothing is possible in the precast because everything is pre-planned and it is pre-calculated and pre-inserted. The whole idea is to bring efficiency, the whole idea is to bring speed, and hence nothing hodgepodge can be done. And after the entire thing is done, you can't do any change in the plan also. The plan has to be frozen right at the beginning. The minute the first precast panel comes, nothing can be changed after that. So the team has to work together right from the initial structural engineer. Even the client has to be on board because the client should approve of the plans that is being thought of. Tomorrow he cannot come and say, I want this to be changed, that to be changed. So everybody has to be there. The typical is the design brief is written out, architect sketch plan is done, conceptual design is done, and then the final design is done. After the final design is done, shop drawings are to be given to the factory, giving all dimensions, all things perfectly in all the drawings with all details, so that the precaster will start precasting. And then there should be erection drawings to the erection specialist as to how, which element has to be erected first. All these elements have to be numbered and so on and so on. So I will not go into this design approach. What is important is that the sections will have to be minimized, and hence it is preferable to have a modular plan so that you will use the same molds repeatedly, you will use the same kind of sections repeatedly. Now, another important question is, should you have a fully precast section, or should you have a fully cast in situ section, or you can have a combination. A combination is definitely possible, but precast, you should try to see maximum of precasting so that all the elements of speed, economy, quality, all of these are built in. So that's about it. And now architecturally also, you can make it very, very beautiful. The layouts have to be a little simpler. Floor to floor heights have to be such that the wall panels can be transported. You know, there are issues in transportation in India. A lot of cables on the road, lot of tree trunks may be there, so many other obstructions to transport the material. So you can't have two tall members which are being transported on the trucks. We will come to that in a little later. So you can see here some large buildings which are built with the advantage of repetition. So the repetition in a large scale project makes precast the ideal choice for the construction. So the details are important, detailing is important, tolerances between the elements are very, very important. If the sizes are not correct, it will just not fit there. So this is something which one has to look at. So I'll skip all of this. I'll quickly take you in another 5 minutes or so through the manufacture, transportation, and direction. You can see this is a typical,
Kangal sir, sorry for the interruption. You
Yes.
can go ahead, sir. So there is no problem. We have kept only one webinar. No next person will come. So
Okay,
you
okay.
let the students can listen to you.
Okay, if they are interested, they will ask questions in the end. So I'm keeping some 10 minutes for that. So now
Okay, sir.
I deliberately avoided design issues because they are still not mature enough to go for the design
No,
issues.
few of
So,
the faculty members are also joined from Kerala, Chennai, and all, because you know at national level. So I think the many people have joined. So I think
yeah.
you can just take a little another
Okay.
10-15 minutes
I
extra.
will,
Nothing wrong in that.
okay, I'll go back five slides and quickly deal with the design issues a little so that, they will also be satisfied. Just 1 minute.
Okay, sir. Okay, sir. Okay.
So when it comes to the design, what is important is the the load flow. So how the vertical load flows is something that one has to visualize properly. So you have to achieve the proper transfer of vertical loads. You must visualize how the load will go from top till the foundation. You must make sure that all the joints are perfect, they are grouted properly, and the sleeves are provided in that particular place. You have to define where the sleeves will be, how they will be filled with grout, and where the the connections will come, where the connections have to be welded, where the connections have to be bolted, and so on. You can see here the double bars in the wall panels which are there. So the next element will come from there, and the dowels will get into a sleeve which is preformed in the top element. Afterwards, grout is done so that there is a continuity in the vertical elements. As far as lateral load path is concerned, most of these are designed as shear walls. So shear walls will be required in both the directions, obviously, to withstand lateral loads, either due to wind or due to earthquake and so on and so forth. And the floor is taken as a diaphragm, which will transfer the horizontal loads to the vertical load carrying members, which are the shear walls made out of the precast elements, which are the wall elements. The structural integrity becomes very important. The shear wall design or the arriving at the bending moments, arriving at the structural things will depend on how the junctions are, whether they are monolithic, whether they are having zero moment capacity and so on. So these are things which can be modeled and it can be analyzed. Building as a whole, and also interstory issues which are there in terms of moments, in terms of drift, in terms of movement and so on. So monolithic wall-to-wall connections are possible, and these are to be done at critical locations. And for inner panels also, sometimes this monolithic wall-to connections is made. So as far as the loads are concerned, the same loads which are there, dead loads, live loads, wind loads, earthquake loads, erection loads. Erection loads are something which are slightly different and a little involved. So people should take care that all the load conditions, and also construction stage analysis needs to be done, because the whole structure is not integrated as you build. So there might be some bending moments, there might be some loads which are due to erection, but there may be no resistance built in. So it's very important to do, construction stage analysis. So when I am at plinth stage, what happens? When I am at lintel stage, what happens? When I am at roof stage, what happens? When I am going to the next floor, and till the load is handled, how the panels are to be supported or temporarily supported or how all of these things will have to be considered by the design engineer as well as the erection engineer. Accidental loads might have to be designed for. Secondary effects due to contraction, expansion, differential settlements, eccentric connections, all of these which are there in normal buildings also will have to be looked at here. So dead load should be assumed in design as per IS 875. Load from lightweight partitions are treated as line loads. Imposed loads for different kinds of occupancy are taken and put in that particular design aspect. Snow loads, if required, can be considered. Wind loads as per 875. Earthquake loads as per 1893, and so on. So load combinations also, just like we do for other buildings, we have to consider here and see which combination gives you maximum stresses and deformation. So it could be dead load imposed load, dead load imposed load, wind load, or earthquake load, dead load, wind or earthquake load, and so on and so forth. Dead load plus erection load will be one new case which will have to be built in. So wind load and earthquake loads code permits you not to act simultaneously. You can take independently and then see which is the one which is causing higher stresses. So now I come back to the manufacturing, which I wanted to talk about. So this is a typical layout of a factory which is producing precast elements. What you will see is that you require large area. You also require a gantry crane to lift the precast members and transport it to the storage yards. So these two elements you will see in this particular photograph. So the plant, we should also have facility for the concrete mixing batching plant and transporting of the concrete from the place where it is done and it is brought in here. So precast concrete machinery basically has concrete feeding machinery with hoppers, machinery for production of concrete products, including machines for handling vibration, and things like that, and curing lines, because where you cast, you may not cure, you may take it elsewhere, so they can use that place for casting further elements. Pelletizers, once you make this number of pieces, you may put them one over the other, pelletize them, and then keep it ready for transportation. Molds are most important because these will have to be very sturdy, and these will have to be, repeatably used. You can't stop a factory midway, so you should be able to use it for 1,000 times, 2,000 times without stopping the factory uh, for minimum maintenance. So molds for production of insulation walls, driveways, and such other things. So this is an overall layout. You can see here the area where concrete is being cast, is being transported, assembly line for reinforcement, placement, doors and windows placement, and so on and so forth, or probably even a pre-stressing yard for hollow core slab extrusion and so on. So this is a typical batching plant. You can see here that concrete mixer drum is there, and then there is a hopper. Now concrete is, in this particular photograph, concrete is being poured onto a belt, and the belt is carrying the concrete inside the factory. Concrete can also be brought using a transit mixer. You can see a truck which has come right inside the factory. You can see here that the reinforcement is being tied at one place, concrete is being placed at some other place. All kinds of activities are happening inside the factory. Now you can see in this particular photograph the uh, pre-stressed cables. The cables are now anchored. This is a pre-tension method. That is, you are stressing the cables and then pouring concrete over it, or casting concrete over it by extrusion or by normal casting. So the structural elements are reinforced, normal reinforcement, or a weld wire mesh, or even a pre-stressing cable. So this is a typical arrangement that you will see. Conventional steel is added for resistance to thermal and other stresses, even if it is a pre-stressed slab. So you can see here a hollow core, casting yard. There are 3, 4 lines that you will see. The center one, you can see the cables. I hope you can see it. The cables are the ones which will be stretched end to end. You can see that some 200 meters the cable is stretched on either side, and then once the cable is stretched, a machine will come and it will extrude concrete, just like it happens in a injection molding factory. The concrete is extruded onto this particular element, which is also encompassing the stretched wire which is there. So once the concrete hardens, you can see that the third line, the extrusion machine is going forward, extruding the concrete. On the right side of that, you will see a completely extruded panel. After the concrete has achieved its required strength, there is a cutting machine which will cut the panels at whatever size that is there, automatically also cutting the wires and transferring the stress by pre-tension. So this length can be 200 to 50 meters, and conventional reinforcing, weld plates, blockouts, lifting loops, all the things are kept in place. Then the concrete is placed there by extrusion or by normal placing. So you can see here the hollow core planks. Hollow core planks may have cross sections varying from circular to oval to even rectangular, and the thickness of the slab depends on the span and the load, as I mentioned. So a typical storage yard, you can see all kinds of panels are stored outside for dispatch. So this is another view of another factory. You can see here the window panels, door panels, the conduits, all of them are already assembled. I hope you can see that. This is the door panel, this is a window panel. You can see the conduits which are going around, pipes, the electrical pipes as well as water supply pipes. Everything is assembled. So this is a system where you can have all things ready. Then the concrete pouring machine will come, which is on the other side, and then this whole thing can be cast wherever it is. There is also another system where this bench itself starts moving towards the concrete placement. So as the bench comes in front of the workers will assemble whatever they are assigned to work. So when it comes in front of, let us say, group A, they will put all the reinforcement in place. When it comes to group B, they will put all the cover blocks in place. Or first they will put the cover blocks, then it will go to reinforcement, then it will go to conduit and so on. So the whole section itself will go from place to place. That is also possible. You can see here reinforcement assembled, the formwork is oiled, everything is ready for casting on. So here you can see panels which are cast. You can see here panels which are now going to the yard for curing or for stacking. The same slab which I showed earlier, which had walls and other things built in. The tables in which this is cast is called a tilting table. So what happens is you cast the slabs horizontally, but when you tilt the table, you can lift the slab, take it out of the mold and carry it like it is shown here. So it is cast horizontally, tilted into vertical, lifted and taken up. Because a slab which is lifted horizontally will experience very heavy bending moment. Now, if it is lifted vertically, you can realize that it is very stiff and hence there will be very high resistance to bending moments. I hope this is clear to you. So, these are called as vertical battery molds. So, the wall panels can also be cured vertically. So, it can be cast vertically, and you can see these pipes which are, feeding steam into the molds, and they are steam cured in standing position. Then you just remove the mold sideways, and you will have the vertical element ready. This is used for casting the whole house, casting the whole unit or pods or walls, columns, and so on and so forth. So this is another large yard where you can see slabs, columns, chechas are all stacked for this is transportation. You can see a vertical slab which is being transported, and the tying of this, connecting this so that it doesn't fall off. You can see that it is organized in the form of an A. If you keep it vertical, it will be much taller. So it is tilted towards each other, is more stable, and also is of lesser height. But if the slab is of much greater height, you may use trucks which are called as low slung trucks. You can see here the slab bottom is almost half to the depth of the tire of the trailer. So still a very tall wall panel is being carried in a vertical position. So the double T is being carried here, a crane which is lifting it and keeping it in the truck. And at the site, the hollow core panels are lifted and kept in place. The machinery which is on top is a very special machinery here. This holds this particular panel by vacuum. So there is no lifting hook. It just lifts it by vacuum and then places it there and releases the vacuum. So that is also possible. Or you can have grips which will hold through the boom of a crane, and then they can be lifted and kept in place. So this is a picture showing the erection of a hollow core slab. The vertical wall panel being lifted is points at which it should be lifted is designed by the engineer, and it has to be lifted only in that place. Otherwise, you may get into some very large undesirable deflections, bending moments, and the panel may break. How do you lift? Whether you lift it by tilting or you lift it by inclining horizontally, again is decided by the erection engineer and the design engineer in discussion. So you can see the whole on the right hand bottom side, the whole side front fascia with all the openings, the whole thing is cast in one and being lifted in place. So you can see here a very large column which is being put in place. The whole building now, entire thing is precast. You can see columns are precast, slabs are precast, beams are precast. All of them are being erected. A huge number of erection equipments like cranes are a must. So joining is the last thing that I want to talk about. Joints are very, very important because the first doubt that anybody will get is when a wind blows or when earthquake happens, will it simply fall apart like pack of cards? No, because you will have to simulate what kind of loads will come at these joints, and you have to design the jointing elements very, very carefully. If it is very difficult to design a jointing element, mechanical jointing element, you can also go for casting joints. So joining of precast concrete elements is an important part. First, the design of it. Second, how it is done in the site. So you can see here two connections, column to column. You can see the connections, how it is done. The top is the precast column, bottom is a precast column. There is a plate here, there is a plate here which is built in into the precast material. In between there is a plate which will, they will put shims between the two, and this plate as well as this plate are welded together. Then automatically both the columns will act as one. So this you can see here that it is welded together, and also there is a provision to bolt. So welding and bolting can be done simultaneously or in isolation. And you can see in the third picture that the area which is the joint area is now dry packed with a grout after the alignment is checked with the bolts and such other things. The second one is a beam to column connection. You can see here that the column with the corbel with all the required reinforcement is already precast. It has welded plates which are cast at certain places where it is going to enmesh with the beam which is coming from the horizontal direction. The beam is also having the reinforcements which are built in with the welded plates cast into the beam. So these two are connected, bolted, welded, and if required, some local connection grouts are also placed. So there are various ways in which you can connect the slab to beam, beam to column, and column to foundation. So all the joints are having multiple systems of connection, and one of the best ways to connect is to cast the junction monolithically with concrete, but of course it will involve a little bit of hassle at the site. Here you can see that there are two, three uh, hollow core slabs placed side by side. Then the screed is placed on top. There is a reinforcement also on top called as the surface reinforcement, and this whole thing will act as one particular slab. So these are some mechanical locks, latch type of panel connector, beam shoes, wire loop boxes, and so on and so forth. So there are various ways in which you can connect. So I have covered, I think, most of the issues that are there in precast and prestressed members apply to a section, right from concepts to design to manufacture to erection to the junctions. So with this, thank you very much. If there are any questions, I would be happy to answer.
Thank you, sir. Thank you very much for your insightful into this precast and pre-stressed concrete structures. I think from the students and faculty and the practicing engineers, they will be surely benefited from this session. And now I would like to ask the participants, if you have any questions, you can ask the questions. So before asking the question, please check whether you have unmuted your mic and ask the question, and mute it immediately, and wait for the speaker to answer to your question, and then you can have a follow-up question. So then I will now I will open the participants to have any question answers.